Okay, so let's continue for our chapter of heat transfer. Okay, so let move on to the new subtopic, which is thermal resistance. Okay, thermal resistance. So we know that our dq over dt, which is the power for the heat energy. So dq over dt is actually equals to the negative thermal conductivity times the cross-sectional area or the surface area and multiplied by the temperature gradient. So this is d theta over dx. So okay, so as for the reminder, this one is the thermal conductivity. So okay, so we know that Ka and this d theta is actually shows the change in temperature between 2 points. So the change in temperature is actually equals to theta 2 minus theta 1. And this and this dx is actually the change in the distance. So I just remain this dx as delta L. So okay. So what if I move this Ka into lower parts? So what I get is basically is theta 2 minus theta 1 divided by the change in L, which is the distance between 2 points. So divided by Ka. So this is still negative, of course. So the negative I substitute into this equation. So what I get is theta 1 minus theta 2 over change in L over Ka. So this is the final equation. Okay, so from this one, which is change in L divided by Ka, is actually equals to our thermal resistance. So this is considered to be the resistance for the heat transfer. So let's say let's observe about this equation. So we know that our thermal resistance is actually equals to change in L divided by Ka. So from this equation, I actually can observe the relation between these three variables. Okay. So from here, I can see that if my cross-sectional area of the wire, let's say my object is the wire, so if the cross-sectional of the cross-sectional area of the wire is smaller, and hence the thermal resistance is higher. So if the length of my wire is high, and hence what I get is the thermal resistance will be higher. So this is the relation between the thermal resistance and the length, and the thermal resistance and the cross-sectional area of the wire. So this is what we meant by the thermal resistance. So let's just move on to another parts. Okay. And so let's proceed to another subtopics, which is the heat conduction. Heat conduction through composite rods of different materials. Different materials. So let's say I have my object 1. So my object 1 has a theta 1. So this object 1 is actually keep in touch to a rod here. So this rod is, of course, is perfectly insulated. So this is my K1. So this rod will be my K1, and this rod is actually attached to the second rod. So this rod as well, perfectly insulated. Okay. So this rod consists of thermal conductivity of K2. So this rod 1 has a length for L1. So this rod has a length for L2. So this the second rod is actually attached to another object which have theta 2. Okay, so we know that for the rod x, so this one is considered to be x and this one is considered to be y. So our rod x, so the rate of heat flow for the rod x is actually equals to negative K1 A d theta over dx. So this is the temperature gradient for, okay, so let me write it properly. So this is the temperature gradient for rod x. And what about rod y? So the rod y has a rate of heat flow which is equals to negative K2 A d theta over dx. So this is the temperature gradient for y. Okay, so let me just erase all this one. Okay, so when all of them is actually keep in touch, and we know that we discussed from the previous chapter, not previous chapter, the previous parts. So the temperature difference is actually will varying at every point of all the rods and the objects. So this will be varied, and for the first second they varying, and the second will also varying, and the third second will also varying. So all of them at every point of the temperature is actually keep varying. So this one shall be my theta 1 and this one shall be my theta 2. So all of them is actually varying until they achieve the steady state. So the steady state, what I mean is the temperature gradient. Okay, so wait, so let me just label all of this. So this one should be my change in x. So that all of them at every point the temperature um, is keep varying at different point until they achieve a steady state. So steady state will actually give us a straight line. So a straight line consists of a constant uh, how should I say, constant temperature gradient. So when the steady state is achieved, my and hence my temperature gradient at every point is actually equal. So this shall be my temperature gradient, which is a straight line. So okay, so let me just observe about it. Yeah, so the temperature gradient at every point is actually equal. So it means that my rate of heat flow is also equal at every point, whether the object is in theta 1 or k1, k2, theta 2, theta 1, all of them here, the rate of heat flow is actually equal, which is dq over dt. Okay, so let me just erase this one. So this is not the point. So the point is, at steady state, the rate of heat flow for every point of the rods and the objects are actually equal. So this is what I aim for. So since the rate of heat flow is equal at steady states, so what I can say that my okay, so this is equation 1 and this is equation 2. So my equation 1 is actually equals to my equation 2. So this is my K1A and this is temperature gradient for rod X and is equal to the rod Y. So this is how we define the rate of heat flow at every point. Okay, so what I have here, okay, so what I have is the rate of heat flow for rod X is the equals to the rate of heat flow at rod Y. So as we observe from this rod, okay, let me draw a rod again. So this is another rod and this is the object theta 2 and this is theta 1 and this is k1 and this is k2. So as we observing this these rods, we can see that there's actually a junction between the rod 1 and rod 2. So this I denote this one, I shall denote this one as theta 3. So alright, so what I have here is actually K1A, so theta 1 minus theta 3, which is the change in temperature. Since the change in temperature at the difference in temperature between the 2 points for every part of these rods and these two objects are equal. So my T1 minus T3 divided by my L1, of course, and this is L2. So this is my L1 and is equal to K2A. So this is my theta 3 minus theta 2, which is the junction between, how should I say, okay. So theta 1 minus theta 3 is actually equals to the theta 3 minus theta 2. So this is L2. Okay. And so since negative can be cancelled and this can be cancelled and cross-sectional area are the same and hence can be cancelled. So what I get is K1 theta 1 minus theta 3 over L1 is equal to K2 theta 3 minus theta 2 over L2. So this is how I get the formula. So in order to express the theta 3 in terms of all of this equation, so what I need to do is, okay, is substitute expand this K1 into the equation. So this is L1 minus K1 theta 3 over L1. So this is K2 theta 3 over L2 minus K2 theta 2 over L2. So what I need to do is actually derive in terms of theta 3. So plus K1 theta 3 over L1. So this one can move to the right side. So the right side I change back to the left side. So since the L3 is our main objective, okay, so K1 theta 1 over L1 plus K2 theta 2 over L2. So factorize the theta 3. So what I have here is K2 over L2 plus K1 over L1. So this is K2 theta 1 over L1 plus K2 theta 2 over L2. So what I have here for theta 3 is actually K2 theta 1 over L1 plus K2 theta 2 over L2. Okay, so divided by K2 over L1 plus K1 over L1. Alright, so this is how we find the temperature of the junction. Okay, so basically this is how we derive the temperature of the junction. So have to note that, so okay, what should I say just now? Okay, so the temperature difference at every point are equal. So this is the utmost important and the main focus for us, so that we are able to derive this theta 1 minus theta 3 and all the equation, and so that we are able to find out the temperature at the junction. So this is how we calculate the temperature at every part, of course. So let's just move on to another part. Okay, so let me just erase all this one. Alright, so okay, so back to the original equation, which is the rate of heat flow for rod K1. So K1 is actually A theta 1 minus theta 3. So okay, so this one shall be my L1, and dq over dt is equal to K2A theta 3 minus theta 2 over L2. So what if I derive this theta 1, the difference in temperature? So theta 1 over theta 3 is actually equals to my dq over dt. So I derive it in the form of the thermal resistance. So this is theta 3 minus theta 2 is equal to dq over dt over K2A over L2. So this is the first equation and this is the second equation. Okay, so let's say the equation 1 plus the equation 2, So the theta 1 minus theta 3 plus the theta 3 minus theta 2. So what we get is basically is theta 1 minus theta 2. So which is the dq over dt over k1a over L1 plus dq over dt over k2a over L2. Okay, so let me just observe for a while. So alright, so let me just simplify it. Okay, and this is L1 over K1A, and this is dq over dt plus L2 over K2A, and this is dq over dt. So let me just write it here, proceed it here. So finally, my dq over dt is equal to the theta 1 minus theta 2 divided by the L1 over K1A plus L2 over K2A. So what I get in this equation is actually the total rate of heat flow between the object 1 and the rod 1, and how should I say, the rate of heat flow all which involving all the object and the rods. So so that's it. So I can finally conclude that. Let me just erase here. So finally I can conclude that my rate of heat flow is actually equals to the temperature difference over the total thermal resistance. So in the form of formula, so theta 1 minus theta 2 is equal to the sum of the resistance. So this is L1 and this is KIA and this is LI, and I start with 1 and this is N, let's say. So this is the general formula for the rate of heat flow for the object which involving the two objects and the rod. So we use the diagram just now as the example. Alright, so we have done for this part. So let me just erase all this one. And this one as well. Alright, so let's just move on to another part, and this is the last part for the heat transfer through the solid or object, and this is the thermal conduction of non-insulated rods. So the non-insulated rod is meant by the rod which is not insulated. So basically, so let's say I have my M and this is my N. Okay, so this rod is actually not insulated. So we know that the insulated rod, the rate of heat flow is there is no heat energy lost to the surroundings. So if the rod is not insulated, So hence what we get is the heat is actually lost to the surroundings. So this is heat lost to the surroundings, and the heat is actually lost from the side of the roads to the surroundings. Okay, so in terms of graph, if the road is insulated, the heat flow is actually flow from the hotter region to the colder region. So, and this is and let's say we have two roads. Okay, so this is the first road, and this will be my second road. And this one will be my theta 2, and this one will be my theta 1. And okay, so let me just L1, and this one shall be L2. And if the road is not insulated, so what we get is okay, is the temperature is actually not decreasingly, how should I describe this, um, decrease in not constant way, which the temperature decrease in the form of curve. So this one is curve as well. So as for the steady state, the temperature is actually decreasing constantly due to the, okay, so this is insulated and this is not insulated. So for the insulated road, the due to the heat is not lost to the surroundings, hence the temperature is actually decreasing from T1 to T2. So my heat is actually flows from T1 to T2 at the steady states. So since the road is actually not insulated, so the temperature is actually varies, not constantly decreasing. So due to the heat is actually lost to the surroundings, and hence the temperature is not in steady states. Okay, so in terms of my temperature gradient, so this is my temperature gradient, and let's say this is my T1. If the So let's say this is the road which is insulated. So we know that the temperature gradient is actually constant throughout the point due to, okay, so this is my theta 1 and this will be my theta 2. Okay, so if the road is insulated, the, okay, this one is my T1 and this one is my L2. So if the road is insulated, the temperature gradient at every point is actually considered the same. So, but in the case of not insulated, the temperature gradient, which is different at every point, shall be varying in the form of curve due to the heat is lost to the surroundings. So this is how we define the temperature gradient and the temperature at every point if the object is not insulated due to the heat lost to the surroundings. So let me denote this one as heat loss. Okay, so this is the final parts for the conduction through the solids. Okay, so we have done for this parts. So let's move on to the new parts, the new subtopics. So for the second way, from the previous video, we talked about the heat can be transferred in the three metals, which is solid, liquid, or gas. So this time we're going to talk about the heat transfer through fluids. So fluids can be gas or liquids. Okay, so for the first one, okay, this one. And for the first one, we are going to talk about the convection. Convection. Okay, so what is actually meant by convection? So convection is actually the transference of heat energy within a fluids. So fluids can be gas or liquids. So okay. When the statement is not done yet, transference of heat energy within a fluid when heated fluids is caused to move away from the source of heat. So this is the definition for convection. Okay, so convection is actually the transference of heat energy within a fluid when heated fluid is caused to move away from the source. So convection basically can divided into two forms. So for the first form, we have natural convection. So for the example of natural convection, so here I got the sea breeze. So let's say this will be my sea breeze, or let me draw a diagram. So this will be my land and this will be my sea. And this, and this shall be the sun. Okay, so in the hot day, in the morning, the air is actually so the land is actually heated up faster than the sea. So since the land is easily get heated up than the sea, and hence the hot air is actually expands and become less dense. So the higher the temperature of the air, so the less denser is the density of the hot air. And since the air keep expanding, and hence it's become less dense and finally will flow it up to the sky. Okay, from this is the hot air. As for the cooler air, So the cooler air has the denser, okay, or dense, which is the denser density. Okay, so since the air has the denser density, and hence it will actually descend to the ground. So this air, this hot air, which is expanding to and flow into outward to the sky, and hence this causes this region, okay, and this region actually become a partial vacuums. So partial vacuum is means that there's no air inside this region, um, due to the hot air is actually expand and flow out into the sky. And okay, so since there is a partial vacuum here, so the air is actually try to balance itself, and hence the wind will blow the air into here to fill up, or should I say occupy, this partial vacuum. And I repeat again, so this warm air expand and flow up into the sky, and this cooler air which has the denser density, so it will actually descend into the ground. So the expanding air, causes this region to, or should I say the land, to be partially vacuum. So the air tries to balance itself, and hence the wind will blow up. The wind will blow up to fill up this partial vacuum, and this process is what we call sea breeze. And this is the process of sea breeze. Okay, so the sea breeze, I can say that the sea breeze is actually the, how should I describe this? From colder region to hotter region. So this is the process of sea breeze. Okay, so since there's a partial vacuum, I repeat again. So since there is a partial vacuum, and hence the cold air tends to spread itself, and hence to occupy this partial vacuum. Okay, so this is the one of the example of natural convection. Okay, so we have done for this parts. And as for another example of natural convection, so what we have is natural convection. So what we have for the other examples, such as hurricane, monsoon wind. So let me see what we have here. And typhoon. So this phenomenon is actually due to the extreme difference in temperature. So if there is exists in the very big difference temperature in the surroundings, let's say our ground is quite hot, and hence the sky is actually has the cold air, which is denser. So due to the expanding of the hot air, like the sea breeze as we discussed from the previous parts, so due to the high temperature of the ground, so extreme high temperature of the ground and the cold temperature of the wind of the sky, so this will actually causes the hurricane or the monsoon wind or the typhoons, which the wind will blow it up in order to occupy the partial vacuums. So this is the partial vacuum. So partial vacuum is due to the expanding of the hot air from the ground to the sky, and this wind will eventually blow it blow it up the land. And if the temperature is actually extreme difference, so this will causes the hurricane or typhoon. So this is the natural phenomenon, or should we say the natural convection process in our surroundings. Alright, so we have done for the natural convection. So let's just look towards the forced convection. So this forced convection is the artificial convection process made by humans. So forced convection is actually meant by the motion of fluid generated by an external source. So this is the forced convection. So what is actually meant by external source? So let's just look out for the example. Okay, so as for my example for the forced convection, so let's say I have a pot. So this pot, I about to use this pot to okay, to cook my water, and this is my water inside the pot. So I supply my heat beneath this pot. Okay, let's say this is my pot. So I supply my heat below this pot. So what can be observed is actually a circular path of the water which is formed, and this as well. So why is this so? This is because, okay, when heat is supplied beneath these pots, so the the temperature of the water is actually below this pot is actually higher. So the higher um, temperature in this region of the water causes this causes the water in this region to be expand. So expanding of the water causes the density of the water in this region, which has higher temperature, to be expand, and hence it will flow to the upper parts. So let's say the heat um, how should I inscribe this one? So let me just write in terms of the sentence. Okay, so when heat is supplied, below the pot, okay, so this will be my sentence. So the heated water is actually expands and becomes less dense, and more buoyant. So more buoyant is actually meant by the water become less denser. Okay, so when heat is applied below the pot, the heater water expand and become less dense and more buoyant. So less dense of the water, which has the higher temperature, will actually flow to the upper region. So let me just write it down. So I divide this region. So this is upper and this is lower. So the heated water at the lower parts will actually flow up to the upper parts. So after after that, the cooler and denser. So the cold water, or should we say the lower temperature of the water, has a higher density. Okay, water near the surface. So near the surface. Okay, the sand, the sands. Okay, so the cooler water, which is at the upper parts, will actually descend due to the higher density compared to the hot water, and hence it will actually descend. So this process is actually repeatedly occur repeatedly. So repeated process causes the hot water and the cold water to be keep changing the direction. So the keep changing in direction causes the water to become in the form of circulation process. So this is the circulation process, which the hot water and the cold water is actually keep changing um, how should I say that? Keep changing the position, which the hot water will move on to the upper parts and the cold water will move on to the lower parts. Okay, so this is the forced convection. Alright, so as for the another example is for the forced convection is actually the air conditioner or the heater. So this is the other example for the forced convection process. Alright, so we have done for the subtopic for convection. So let's just move on to another parts. So I believe this shall be our last part, if I'm not mistaken. Okay, let me check for a while. Yes, this will be our last part, which is the thermal radiation. Alright, so what is actually meant by thermal radiation? So thermal radiation is defined as the energy, or we can say as heat energy emitted by matter. So matter is meant by the atoms as, so this will be my keywords, electromagnetic wave. So thermal radiation is actually defined as the energy emitted by matter, which is atoms, as electromagnetic wave. So um, for more simple explanation, the heat is actually travel in the form of wave. So this is how this is another transference of heat energy. One of the how should I inscribe this one? One of the easiest and the fastest way for the transference of heat energy compared to the transfer of heat through solids or liquid or fluids as we discussed from the previous parts. Okay, so this is the definition. So let's talk about the property of the thermal radiation. So thermal radiation, so for the first one, it is actually can propagate through vacuum. So this is the first property of the thermal radiation. So in the outer space, the heat energy from the sun. So this shall be the outer space. So the heat energy from the sun is actually can travel to the outer space in the form of electromagnetic wave. So we know that our outer space is actually the vacuum. So this is the reason why the heat energy of the sun can be traveled through the outer space and approach to our Earth. Alright, so this is the first inscription. As for the second description, the thermal radiation is actually um, in the form of random movement random movement random movement of atoms, okay, and molecules in metal. Since in metal, so since they are charged particles, so um, so electromagnetic wave is actually the movement of atoms, not atoms, we should say that the random movement of charged particles. So this is the second property. Okay. So since they are able to move randomly, so since they can move randomly, hence um, the movement is in the results of electromagnetic wave. Magnetic electromagnetic wave. So since the electromagnetic wave cannot be influenced by the surroundings, the property of the surroundings, such as the outer space or inside the earth, which consists of fluid. So I can say that the electromagnetic wave does not require the fluid to propagate. That is why we can say that the electromagnetic wave can actually propagate through vacuums. So since they are charged particles and their movement is actually random, and hence the result of their movement is actually in the form of electromagnetic wave. So this is the properties, the main properties for thermal radiation. Okay, so this is, let me erase all this one. Okay, just like so. So since the thermal radiation is in the form of electromagnetic wave, and hence is actually, okay, so it actually follows the law of reflection. So since the I repeat again. So since the thermal radiation is in the form of wave, so it is, how should I say that? It will follow the law of reflection. So in order to prove that, so we conduct an experiment. So this is the screen. So this is the circular tube. So I have my circular tube. So this is another circular tube. So this is the bulb, which consists of high temperature bulb. So my temperature is high, and we know that um, the radiation of heat is actually travel in this way. So okay. So what we have is the thermal radiation is actually travel in this way. So based on the law of reflection, the angle of incidence is actually equals to my angle of reflection. So let me just draw this one properly. So okay, never mind, it's okay. So um, so my angle of incidence is actually equals to my angle of reflection. So let's say for another parts, I have a galvanometer and I have a wire. So this small wire is actually called the thermal pile. So this thermal pile is actually used to detect the thermal radiation. So this angle of incidence can actually so this angle of incidence, the tube for circular tube of this angle of incidence can be varied, and this one should not be circular tube, and this one should be the cylindrical tube. Cylindrical. So the cylindrical tube for the region of angle of incidence can be varied, but the cylindrical cube for the angle of reflection remain constant. So this one can be varied, and since the cylindrical tube for the angle of incidence is varying, so the deflection of the galvanometer, the deflection for galvanometer will be different due to the detection of thermal radiation by thermal pile is different. So when the thermal pile detect the maximum thermal radiation, it means that the angle of incidence is actually equals to angle of incidence is actually equals to angle of reflection. So in this case, the thermal pile detect the thermal radiation is actually maximum. So from this experiment, we can conclude that the thermal radiation, which is in the form of electromagnetic wave, is actually follows the law of reflection. So since it is the form of wave, so hence the law of reflection must be followed. Okay, so this is the first part. So let's just move on to our last part of this chapter, and this part is also extremely important. So let's just move on to the Boltzmann Stefan Boltzmann law. Stefan Boltzmann law. BOLTZ. So this is okay. So BOLTZ. So Stefan Boltzmann law is actually states that the total energy radiated per unit surface area of a black body, so per unit time is directly proportional to the fourth power of the black body's absolute temperature of the black body's absolute temperature. So this is the definition for Stefan Boltzmann law, which states that the total energy radiated per unit surface area of the body per unit time is directly proportional to the fourth power of the black body absolute temperature. So in the form of equation, so dq over dt, which is the total energy per unit time, times per unit surface area, of course, is actually directly proportional to our fourth power of the black body absolute temperature. Okay, so if I derive this one, if I move this surface area to the opposite parts, so what I get is actually directly proportional to the AT4. So in the form of equation, what we have is actually equals to sigma AT4. So this sigma is actually equals to the Stefan Boltzmann constant. So this constant is actually equals to is equals to 5.67 times 10 to the power negative 6 W M negative 2 K negative 4. So this is the definition of Stefan Boltzmann law. Okay, so this is so this is for per surface area. So what if I move this surface area to the opposite part? So what I get is the power radiated, which is dq over dt, is equals to the sigma AT4. So sigma is the Stefan Boltzmann constant. So this A is actually the surface area of the black body. So T is the absolute temperature for the black body. Okay, so this is the definition. So let's discuss the properties of black body. So what we have for the black body, so let me just erase this one first. Okay, this one as well. So actually, what do we have for the properties of black body? So black body is actually the body that absorb totally all of radiation of any wavelength which fall on it. Okay. So if it absorbs totally all of radiation of any wavelength which fall on it, it will also admit all the possible wavelength, all the wavelengths, all of wavelength out of it. So the wavelength. So let's say this is my black body. So let's say my radiation, which has 50 degrees Celsius, fall on it. The surrounding temperature of the thermal radiation is actually 50 degrees Celsius. So the black body is actually will absorb all the possible wavelength, which is 50 degrees Celsius from it. So finally, the temperature of the black body shall be 50 degrees Celsius. So if the black body is about to emit all the wavelength, so initially it has the temperature of 50 degrees Celsius. So what will it emit is actually the radiation of 50 degrees Celsius. So it will totally absorb all the possible radiation which fall on it. It will also emit all the possible wavelength inside it. Okay, so this is the black body. So what about the other color which is besides black body? So let's say I have a gray body. Gray body. So gray body does not absorb all the incidence, all the incidence wavelengths, or I should say radiation, and admits the less total energy than black body. So for the other colors, let's say gray body will not absorb all the incident wavelength, all, or should we say all the possible wavelength which fall on it, and it will also do not admit the um how should we say do not admit the total energy which it absorb initially. So the energy will not admit and hence admit totally, and hence the total energy that admitted is actually less than the black body. So let me give an example here. So let me just erase this one. Okay. So let me just erase this one as well. So let's say I have my gray body. So this will be my gray body. So let's say the thermal radiation is actually 50 degrees Celsius. So what will it absorb more possibly is actually less than 50 degrees Celsius. So let's say the temperature of this gray body is actually 42 degrees Celsius. So it is not necessary for the gray body to absorb all the possible wavelengths surrounding it. So what we have here is actually the 42 degrees Celsius. So after absorbing, there will be emitting. So the total energy which is emitted. So the total energy which is emitted is actually 42 degrees Celsius. So this 42 degrees Celsius indicates that the radiation, the energy emitted, uh, the heat energy, or should we say the thermal radiation emitted, the total energy is actually less than 50 degrees Celsius. So this 50 degrees Celsius is actually the energy or total, not total, or the thermal radiation emitted by the black body. So this is what we meant by the sentence, which is admits the less total energy than black body. Okay, so we have done for the description. Okay, so let's just move on to the equation. So as for the gray body, so this is the gray body. So since the total energy emitted is actually less than the total energy emitted by the black body, so I can say that the emissivity of the gray body is actually less than 1. So the emissivity for the black body is actually equals to 1. So this is black body. So I can say that the power radiated by the gray body is actually equals to E sigma AT4. So this E is actually the equals to the emissivity. Emissivity, and this is the Stefan Boltzmann constant, and this is the surface area, and this is the absolute temperature of the gray body. Alright, so that's it for the equation. So as in this part, and let's just move on to the last part. So the last part also relate to this equation. So for the last part, and we know that a body is actually will radiate the heat energy to the surroundings. So if the surroundings and this body is actually in thermodynamic equilibrium. So thermodynamic equilibrium is actually similar to the meaning of thermal equilibrium, which is the surrounding temperature is equal to the temperature of the body. Okay, so in this case, I can say that my emissivity is actually equals to the absorptivity. So the heat absorbed is actually equals to the heat emitted by the body. So so let me just erase this one. So um what if the body and the surroundings not is in the status not thermodynamic equilibrium? Dynamic equilibrium. So if the surroundings temperature and the temperature of the body are not the same, and hence there will be a the net power radiated by the body. So hence I can conclude that my net power which is emitted is actually equals to the power of absorbed. So I repeat again. So if the object and the surrounding temperature is actually in the form of thermodynamic in equilibrium, so there will be a net power which is equals to the power emitted is equals minus the power absorbed. So this is okay. So based on the equation of Stefan Boltzmann constant, so what we get is actually equals to E sigma AT4, and this is admit minus E sigma AT4, and this is absorb. So since all of these distance constant are the same, and it's sigma A, and what I can do is actually factorize it out. So T4 absorb. So finally, this is the net power we get for the difference in temperature between our object and the surrounding temperature. Alright, so that's it for all the parts of the chapter of heat transfer. So we have done for all the discussion for this chapter. So if there is any question need to be asked, please comment below this video, and I'll see you next time. Thank you. Bye.